Good evening, folks. My name is Micah Casteel. I'll be talking today about high temperature electrolysis here at Idaho National Lab. We're going to go through some of the fundamentals as well as talk about where we see it going for the future. Sorry I couldn't make it today. There's a brief snafu with the travel arrangements. I'm glad that I can talk to you about it, at least via the magic of the internet. So with that, we're going to go ahead and start with a little bit about INL directly. If you're like me, maybe 3 years ago or so, I knew very little about what INL does, how big INL is, and all those sorts of things. And it's a much bigger lab than I might have expected. Idaho National Lab takes up a similar space that to Rhode Island, actually. It's huge. We have about 890 square miles in the desert with half a dozen different facilities kind of scattered throughout, as well as a relatively large campus here in Idaho Falls, the town itself. This particular slide is a little bit outdated. We're closer to 6,000 staff at this point, and growing all the time. And because we have such a large lab, and we are a nuclear lab, we are thinking very seriously about this idea of net zero, and both from the research perspective, but mostly how we can dog food our own systems. As you might expect with such a large facility that's based out in the middle of nowhere, we have quite a number of vehicles that are required to operate such a large facility. In fact, we have somewhere between 60 and 80 coaches that are running around every single day, transporting personnel to various facilities, reducing the amount of miles that folks are putting on their personal cars. But in order to meet net zero, even within our own lab, we have to address all of those emissions. And so we're thinking about things like geothermal and hydrogen and batteries and transportation, wind, solar, and micronuclear, both from a research perspective, but really as an enabling perspective. We both have the bless and the responsibility to address these things at scale, and that's really how our lab has been developed. Looking in terms of things that we do here in town to really connect all those things together, this is our Integrated Energy Systems Lab. And this is just a brief picture about what you can see. It's actually spilled out onto the lawn at this point. And this is where we really work hard to connect all these different energy technologies together. So you can see some energy storage here. We've got high-speed vehicle charging. There's some cyber security investigations going on right now, looking at how vehicles charge and how those might be connected to the grid and to the internet. We have high temperature electrolysis. We have non-nuclear experimental test beds. We have thermal distribution, real-time grid simulation, microgrids, power emulation, and all kinds of other miscellaneous things within this one space. And they're all connected together, so you can really investigate how they interact with one another. In fact, we have systems that allow us to simulate nuclear facilities and then thermally connect them and electrically connect them to facilities to produce hydrogen. And those are the sorts of creative and interesting things that we can do with a lab that's this interconnected. Speaking specifically about hydrogen, our hydrogen portfolio is relatively large and has been going on for 20-something years at this point. We started back in the nuclear hydrogen era, and we've moved into a lot of the newer developments at this point. So we start very, very small. And so from us, starting small for us is in the materials development field. Most of our materials development is actually on protonic conducting ceramic materials at this point. But as we start moving into more commercial materials, we have the H2Nu consortium, and that's when we're starting to look at degradation, fundamental mechanisms that we can investigate ways to improve commercial systems, understand how commercial systems fail, and really advance the technology. As you start scaling up into the short stacks and cell testing, even larger stack testing, that's when we start doing commercial validation work. And so we'll look at some of that data. But really, we have a facility that's available and open for use by commercial entities, whether those domestic or international, to be able to verify how these systems work as you might want them to. And then from there, we scale into what we kind of call a pilot plant demonstration level. So that's hundreds of kilowatts to even megawatts in terms of demonstrating how these systems work at scale. That's both electrical and thermal integration into full, complete systems. We're going to take a quick step back and talk about electrolysis from a fundamental level, because I really can't emphasize it enough. Electrolysis is affordable magic. We're really taking something that nobody wants and turning it into something that's extremely valuable. And we have quite a bit of flexibility in how we do those integrations and make those conversions. And so I always like to just take a step and think about how we can do this and what's possible with this technology. So there's two general routes that we go from liquid water into hydrogen. There's the low temperature route and the high temperature route. Low temperature, really, we start thinking about higher heating value. And so that's, on the order of 39 and a bit kilowatt hours per kilogram. Versus the high temperature route, which is really thinking more about the lower heating value. And so the reason that's the case is we can separate out the vaporization piece and do that thermally. So we can take liquid water, we can vaporize it into steam, and then operate on that. And much like running in the reverse of combustion, this allows us to use less electrical energy. Now, as a brief reminder, everything you see on this screen are rough thermodynamic minimums. Of course, real reactions will exhibit losses. As my thermodynamics teacher used to say, you can't get something for nothing, and you can't even break even. And we'll talk a little bit more about that as we keep moving forward. A conventional high temperature electrolysis system looks something like this. We have what's called a cold balance of plant. Cold balance of plant is all of your reactive processing. So you're bringing in water, you're purifying it, you're vaporizing it into steam, you bring in some air, and then all of those things are fed into the hot module. Now, I put the steam generation in the cold balance of plant, and there's a good reason. When we think about making steam, we think about low-grade steam, something on the order of 150 degrees Celsius. And that's important because 150 degrees Celsius is relatively inexpensive steam. In fact, some places it can be free. But in general, you can think about thermal energy to be roughly a third the price of electrical energy. Once we have all of our reactants prepped, they feed into the hot module, hot balance of plant. The first thing they're going to do is go through a series of heat exchangers. We may have some trim heaters at the very end, and then we feed those reactants into the stack array itself. The stack array is operating about 750 degrees C. And again, the first question I get when I give tours about our systems is, well, where did that come from? Well, we had to heat the system up once, and then we operate at the thermal neutral point. And as long as you have good heat exchangers, you need very little thermal energy input to get back up to 750 degrees C, because the mass going in is the same as the mass going out. So a good heat exchanger will get you most of the way there. That's where we need to put in the electrical energy. Finally, we're going to have some products processing at the back end, some electrical energy for pumps, compressors, blowers, etc. And then we've got to pull some thermal energy out to separate our hydrogen and water. What does that look like in terms of the I curves? Well, this is some examples of practical cell voltage. And I say practical here, this is just a rough perusal of the literature. The exact intercepts between the cell voltage on the x-axis 0 is dependent on what your overall composition is. So a more realistic system level composition for solid oxide electrolysis is going to be closer to 0.9 volts at open circuit. And then those are going to go up in voltage, obviously, as you go up in current density. Again, a realistic system curve is going to go up much more rapidly, much higher slope than you see on this chart. But for purposes of comparison, what I really want to talk about is the water thermal neutral voltage and the steam thermal neutral voltage. As you'll notice, there's a fair bit of operating possible for solid oxide electrolysis below the steam thermal neutral voltage. And what's tricky about that is essentially, since operating voltage has a direct effect on system efficiency, that's greater than 100% electrical efficiency below that line. And of course, we can't violate thermodynamics, so we still have to supply that energy somehow, and we have to supply extra because of the second law. But we can do that with thermal energy input. Realistically speaking, I don't have a whole lot of heat at 750 degrees Celsius, and so we tend to pick operating at the thermal neutral voltage, and that means we don't need a lot of high-grade heat. We just operate at the stack with no heat generation or consumption, and then we supply thermal energy to make steam. Of course, we're going to have to supply all the energy, but when you look at the electrical energy consumed by the cell or stack, they only consume about 34 kilowatt hours per kilogram DC. We have lots of evidence of that all the way from the button cell up to relatively large stacks, and that's a really interesting starting place, because that means basically everything after that is gravy. If we can get low price thermal energy, we have the opportunity to make some very low cost hydrogen. Looking at the small scale, I don't have a good slide on materials development, but you can assume it more or less falls into here, looking at proton development. But this is in terms of doing materials development. We have quite a large number of button cell test facilities, single cell, small stacks, pressurized stacks, to investigate the performance of cells, degradation of cells, these sorts of things. And we have all the standard methods you might imagine: accelerated stress protocols, long-term degradation, doing a waveform type interrogation, materials development, those sorts of things. And we can do all these, on kind of a broad league scale in a long time period. A lot of this technology, or a lot of this, test infrastructure gets sucked up into things like the H2New consortium. And this is where we're specifically looking at degradation over time. You can see the impact of degradation on the VI curve. Over time, we start seeing that relatively shallow slope become steeper and steeper and steeper. And of course, in H2New, we're specifically trying to make degradation happen. And so if you look at that right-hand graph, you can see the impacts of water purity on cell degradation. One of the things that's interesting in electrolysis is that we don't have fuel anymore. We have very little air on the air sweep side. And so things like contaminants to your water system actually drive a fair bit of degradation. And so we're really diving into how does that work when you're using a boiler or a bubbler or some other steam generation capability. And what do we need to watch for in terms of creating clean water to send into these systems. Once we start scaling up the length scale, we start thinking about commercial stack testing. This is more validation work. And this is the sort of thing that we've done now for several years, where we bring commercial vendors and we test their facilities, or their stacks, and then we can work together with them to publish that data. If you're suggesting that you want to buy several megawatts, potentially even gigawatts of a component, you'd like to have third-party validation that works like it says. So this is an example of some test data that we have from Fuel Cell Energy. You can see their small stack up there on the upper hand right. And it's run for a little over 2,000 hours now. You can see some degradation graphic on the right. Unfortunately, as you look at that, it's a steady constant current, correct? So the green line is current, the blue line is voltage. Voltage is actually going down, so it's technically improving ever so slightly over time. And this is more or less how it's looked for the last 1,000 hours. It's a relatively boring test, which we absolutely love seeing. No discernible degradation to speak of. What's also kind of interesting is that's sitting at roughly 34 kilowatt hours per kilogram DC. So that's roughly at 99% efficiency right now, and has been for the last 2,000 hours. And that's kind of par for the course for what we're seeing with these high temperature systems. They run really, really well, surprisingly well, in fact. The other thing that's really different about these systems compared to, say, a solid oxide fuel cell is how rapidly we can ramp them up and down. And so you can see on the left-hand side, this is an example of a current ramp where we walked all the way down and all the way back up in a little less than 10 minutes. And in fact, we've repeated the same test in about a minute. And you can see the voltage response right as you'd expect. And actually, there's a little bit of a peak there because we actually cooled the stack ever so slightly during that operation below thermal neutral voltage. As you might imagine, it's endothermic. And so it's getting that energy from somewhere. And in fact, it's cooling the stack to get it. This is something we've seen both at the cell and the system level, is that we can ramp these systems far faster than we used to be able to ramp the fuel cells. And it's just a function of a much, much easier operating condition. So in this particular case, there's no thermal gradients to speak of. These systems are very, very stable across all of their loading. Now, if you go a little bit bigger than this, you can start thinking about putting a system or a stack or hot module into our 50 kilowatt facilities. We have 2 of these facilities. One of them is set up for reversible operation. It's accepting stacks from Oxygen Energy here, well, any day now. And then we have another one coming online soon. And this is just really responding to the fuel cell industry is asking for bigger stacks to be tested and validated. And so we wanted to be able to support that, and also be able to support things like hot modules. So if somebody had a module, they'd be able to bolt it up directly to our balance of plant and be able to test their module in our system. These are coming online soon, and these are also ones that we've designed to be open access. So if we wanted to ever do something like co-electrolysis, reversible operation, chemical synthesis, these are easily modifiable to accept new unit operations kind of on an as-needed basis. Walking back to the system diagram. So we've talked a little bit about the things inside the stack array and a little bit of the heat recovery. So the question is, what happens when we start bringing in larger systems, right? We want to be able to demonstrate that they can actually operate with electrical input and steam on the order of 150 degrees Celsius. And the reason we want to do that is that you start thinking about these systems in terms of a larger facility, let's say a power plant. And we have the potential here in a thermal generation facility to get thermal power directly. So a small nuclear facility, a chemical refinery, even a natural gas plant, they have thermal energy and electrical energy available. And that offers some really interesting possibilities in terms of how much electrical energy is needed to create that hydrogen. As I mentioned before, thermal energy is about a third the cost of electrical energy, and sometimes it's even cheaper than that. And so because about 80% of your cost of hydrogen is the energy input, this offers a potential for tremendous savings in the overall output, what hydrogen is going to end up costing. In terms of testing commercial systems, so at this point, we've been testing a Bloom Energy commercial system for a little over 5,000 hours. I think it's closer to 6,000 hours. And it's been similarly very boring, in fact. You can see degradation is more or less non-existent. The system's been operating almost identically at 37.5 kilowatt hours per kilogram DC input for the life of the plant. Now, of course, we're paying for the steam. We are also paying the rectifier losses, and we're also paying for heat trace requirements to get steam to it. But even when you account for all those things, this is a very, very efficient system. We're talking mid-40s in terms of kilowatt hours per kilogram. It's been very, very stable. The things that we tend to run into with these larger systems, actually things like grid instabilities. As the grids go up and down, inverters, rectifiers struggle with those sorts of issues. Things like dealing with environmental issues, very, very cold situations. We have steam running around outside. That can become a challenge. But the actual box itself is extremely reliable. It's been very, very productive. And the other thing is, I mentioned back in the stack testing, is dynamic loading capabilities of the systems are tremendous. This system has also gone 0 to 10 or 100% to 0 and back again in a little less than 10 minutes. And that's just very, very impressive in terms of how fast these large systems can turn on and off. And that allows them to be able to support the grid in future operations. Thinking a little bigger in terms of going all the way from the inputs to the final product, we have other facilities that are coming online at any given moment. This particular facility is taking a 250 kilowatt SOEC from fuel cell energy. We'll be providing the steam and the power. It'll be reducing hydrogen, and then we'll be taking it directly to compress, purify, store, and dispense into a hydrogen fuel cell electric vehicle coach. Now, this is a little bit of an outdated graph. It's got some older concepts on it than what's currently being built. But this is being built right now with the intention of operating several coaches running back and forth to our site using high temperature electrolysis produced hydrogen. And that's a pretty exciting development, because that means that conceptually this can serve as a prototype for what we will need in the future to green up our remaining coaches, right? I said we had something on the order of 80 coaches that are going to have to be greened up. And due to the fact that we have such a large area, we have things like wildfires, snowstorms, etc. We need the resilience that hydrogen gives us in terms of operating these systems year-round in a safe and resilient fashion. So moving even larger than this, we started thinking about, so what's next for high temperature electrolysis? How are we going to move this technology forward? And I talked a little bit about our cell, our stack testing, and our system testing. And we can all imagine the future where we have gigawatts of electrolysis deployed. But what we started noticing, both internally and when we talked to other energy users, is there's this gap. That gap is somewhere between 2 and 10 megawatts, where you've demonstrated a 100 kilowatt system at a national level. That's great, but I want to buy a gigawatt of this stuff. And so how do we make that jump? And so what we've determined is that we really need to address that gap, both for our own usage, but also for the broader industry. And so we've developed the idea of the Energy Technology Proving Ground. This is a scalable system that's actually being built right now. In the center of this system is a 10 megawatt electrolysis proving facility. And so this will have boilers, this will have power, this will have concrete laydown pads to bring in megawatt class facilities, megawatt class solid oxide systems to start producing hydrogen at scale. We're talking up to about 6 tons a day hydrogen production. And that can feed any number of things, right? We talked about chemicals production. We could have a small pilot ammonia facility here, producing tons per day. We could have a methanol facility. We could have steel production. Any number of things can be done at this facility out in the desert because it's in the middle of nowhere, and that's a really exciting possibility. We have all the land you could possibly want. And so you can imagine things like the travel center of the future. You can imagine a very large chemical pilot plant. There's lots of possibilities. And because we're one of the nuclear power labs, this allows us to really integrate nuclear facilities. So we have a microreactor testing facility right next door that would allow us to tie both electrical and thermal inputs into this large facility. And that offers a whole lot of possibilities for really rethinking, how do we make chemicals? How do we make materials? Rather than digging them up out of the ground, this is a possibility that we can actually start synthesizing things at scale using green energy. And we need that for our own use, but we also need that for the broader industry. And this is a pretty exciting thing that's being built right now. With that, I'd be normally opening up for any questions, because as this is a recorded interview, as it were, I'm going to go ahead and put up emails on the screen that you can reach out to if you have any questions about these things. I left Dr. Dong Ding's email there. He is running all of our protonic cell generation work. So if you have any questions about the modern ceramic materials, you can reach out to him. I'm taking care of all of our cell and system testing. You reach out to me at Micah Casteel at inl.gov. And then if you want anything to do with the Energy Technology Proving Ground, your best contact is going to be Christopher Wright at inl.gov. And with that, thank you for your time, and good luck on the rest of the seminar. Thank you.